Hi everyone, my name is Lily. Later in the video you will meet my other teammates, but we chose for our project to focus on the ropes with mass problem. So the statement we were given was, until now, you've been making the assumption that ropes are massless. We are asked to relax this assumption to consider ropes that have a constant mass density. Consider how this would impact fundamental real-world situations we have considered, such as a rope to pull a sled across a frictionless surface, or connecting two massive objects with a rope passing over a massive pulley, or massless pulley, sorry. We explore several different examples throughout today's presentation. But from what we were given, we will be examining a problem and several problems throughout the presentation today where the rope now has a mass. And we'll be looking at the similarities and differences from a problem where we're given a rope that has mass versus a rope that does not have mass. And so I'm going to just start right in with an example. On the left here, we're given a diagram of two blocks with one a mass of 10 kilograms and one with a mass of 7 kilograms hanging together by a string that is 7 kilograms in weight. So this is a problem where the rope has mass. We also know that there's an applied force of 350 newtons pulling upwards. I have shown the free body diagram of the block and the free body diagram of the rope. I don't have a diagram of the 7 kilogram block because I really just wanted to focus on how in this example we are going to examine a problem where when the rope has mass, what the difference is and why it has its own free body diagram. So we can see that there's this 10 kilogram block. It has, of course, the force of gravity acting upon it. We have a force of tension on the block by the rope pulling downwards, and then of course that applied force or that normal force, of course, and 350 newtons pulling upwards. Then we also have that free body diagram of the rope. That is going to be, you can see that we have that same force of gravity pulling downwards on the rope. Now we have two forces of tension acting, one is acting upwards and one is acting downwards. Both are on the block by the rope. One is acting on the 10 kilogram block and one is acting on the 7 kilogram block. So now we're going to look at a diagram where the rope does not have mass and what is the difference. And as you can see here, there's no free body diagram for the rope. Since it's massless, it can be taken, it doesn't need to be taken into account. And it doesn't need to have its own free body diagram since it does not have any mass associated with it. So here we have the free body diagram of the 10 kilogram block and the free body diagram of the 7 kilogram block. Both are very similar. The 10 kilogram block free body diagram does not change from the one above. We just do not take into consideration the mass of the rope since it's 0. And so we still have that force of tension pulling down. We have that normal force pulling upwards and that force of gravity pulling downwards in the 10 kilogram block. And on the 7 kilogram block, we have a force of tension, of course, from the rope and the block pulling upwards because that 7 kilogram block is at the bottom of that rope. And then we also have that normal force of 350 newtons pulling upwards, same as the 10 kilogram block. And then we have that force of gravity pulling downwards. So now let's look at the similarities and differences between this example and why it's different, why that actually happens. But looking at some similarities first, we do know that both of when the rope has mass and when the rope does not have mass, it still has a force of gravity pulling downwards on it on the system. With both of those, we know that the mass of both blocks both include the mass of both blocks in regard to tension. So we do know that regardless if the rope has mass or the rope does not have mass, we'll still be finding the force of tension. Nothing changes there. The thing that does change is that now we need to add that mass in the equation for finding the tension of the string. So if we're asked to find the tension of the string, or not the tension of the string, the tension of the rope, we would need to consider the mass of that rope in relation to that force because now it's important to know that. And we wouldn't be able to find the tension without knowing that mass, because normally we're inferring, or we're just saying, we're making the assumption that the rope rope's mass is zero, so it's just taken on, it's not taken into account. But now that it is, it will be needed to be taken into consideration when solving that for that equation. Um, now the rope is now considered in the free body diagram. We saw that as the example. All you have to do is make a free body diagram now for the rope as well. So instead of having regular two system in the example that was given, we would now have three systems, because now we have that rope included as well. We have also that net external force will be different due to the added mass of the ropes. Kind of got into that earlier. Again, that rope now has its own mass. It has its own acceleration, has its own force. So yeah.
Adapting the model. Since we're now considering the mass of the rope problems, our model needs to change to account for this, specifically when looking at acceleration and tension. For problems such as the one mentioned above, assuming that the rope is massless allows you to ignore its mass when calculating the acceleration of an object or the tension in a rope. The issue is that in the real world, ropes have mass, and to gain a more accurate representation of what's going on, the mass needs to be included. A rope with mass both affects horizontal and vertical situations that change how we approach each problem. In the instance of an extended horizontal rope, there won't only be a force applied to it in the horizontal direction, since gravity will act on its center of mass, pulling down on the rope ever so slightly, depending on the mass. This would also mean that some of the applied force to a rope would have to be in the vertical direction to keep the rope in equilibrium. The takeaway from this is that when considering a rope mass, the actual force felt on an object through the rope horizontally will be less than the force initially applied to the rope, since a portion of the force is also applied vertically. Shifting to the vertical situation, tension created in the rope won't only rely on the force applied to the end of the rope, like a hanging weight, for example. The mass of the rope itself will also contribute to the tension, as gravity is now acting a force on the rope itself, plus the force of the hanging weight. In situations where the rope is very light, the two models will be very close to each other. But the larger the rope gets, the further apart these two models will become, because gravity is now applying a larger force on the rope itself.
So as for the sense making for ropes with mass, specifically this sled problem here, in the given sled diagram or free body diagram of the sled problem, we can see that force tension is going to be the force that is affected by a rope having mass instead of it being massless, because we're assuming that rope is also coming from the direction of force tension. So if we also make the assumption that the rope is still inextensible and it has a constant non-zero mass density that we assumed in the given statement of the problem, then the force of tension in the system overall would increase uh, because the mass of the rope gets included in the tension formula that is shown here on the left. So this formula is standard for what we normally use to calculate tension. It's just T equals M total times G plus M total times A, or MG plus MA. So M total is usually just the mass of the system, but when we assume the rope has a mass now, we have to take that previously massless rope into account in the overall mass of the entire system, not just the system of the sled. Then for the other variables, G is the acceleration due to gravity and A is the acceleration of the system. So when a rope has a non-zero mass in the sled problem, the sled's acceleration will decrease and the tension of the rope actually increases due to the initial inertia and resistance introduced by the mass of the rope. And the exact quantitative impact would depend on the specific characteristics of the system and the distribution of the rope's mass, if that makes sense. All right, and as for the real world context of this problem, uh, when you're calculating systems in the real world involving pulleys or tension, a rope cannot physically be massless. So, in many physics problems involving tension, we assume the rope or the cable is massless to simplify the calculations, and this assumption allows us to focus on the forces acting on the objects at the ends of the rope without having to consider the distribution of mass along the rope or its effect on like tension. So if the rope has mass, it would contribute to the tension by adding an additional force due to weight, as seen in the previous slide about sense making. And this would complicate the analysis and make calculations a lot more difficult, which is why we haven't been given those problems. However, in situations where the mass of a rope is significant, it would need to take into account uh, the mass of the rope in order to accurately determine the tension of the rope. And some real world examples of this are like elevators or amusement park rides, where the tension of the rope would definitely matter for like the safety of others. And the engineering applications, like an elevator, measuring a rope with mass is crucial for ensuring the accurate calculation of tension forces, allowing the designers to optimize the elevator's performance and safety by accounting for the mass distribution along the length of the rope. And for the designing amusement park rides, like engineers have to measure the ropes, uh, accounting for mass to precisely understand the impact of acceleration and tension forces, basically ensuring that the rides meet any safety standards and making just the ride safe for people. If you know how it's going to affect or how the ride's behavior is going to be affected by the tension of the rope, then that is something that we need to be taken into account.
Alrighty, and for the reflection, um, looking over all of the assignments that we've done this term, there hasn't really been a problem where we have looked at a system with a rope that or a string that has a mass. I took a pretty deep dive trying to figure out some problem that I could dig up that was very similar or had something else had a mass. And so I looked at a lot of the studios that we did, just kind of going through them. There wasn't a whole bunch, but I did find one in the homework activity and then one in a studio where we were looking at blocks that were connected by a rope and had a pulley usually involved. And both the homework and the studio looked at a very similar problem to what the diagram shows to the right there. So overall, the assignment was a cumulative project focused on looking at when ropes have mass and considering a problem where a rope or set of ropes have mass, which does draw some similarities to the homework and studio questions, but also draws some differences. A lot of the homework problems we were solving for the mass of a block or the acceleration of the mass and the pulley. In that homework 3 activity, it said the question asked and told us that we had two massive blocks, which is shown by the figure there, connected to each other by a rope over a pulley with a non-zero mass. So there we know that the pulley has a mass. We don't know what it is, but we do know that it is zero or that we know that it is not zero. And then we can, from all of that information, find the acceleration of both masses. So mass 1 and mass 2 to the right there, and then the pulley, which is considered as mass 3 in the diagram as well. And so I thought that one was kind of similar. It's not where the string has mass, but another object in the system besides the blocks now has a mass as well. Studio number 3, activity 3.1 also had very similar problem. We were asked to find the angular acceleration of the pulley, and it's 3 different interactions within the system. From that, we knew that the pulley had mass. Again, not a problem where the stringer ropes have mass, but just another part where there's another added aspect to the system, where it's not just the massive, or where it's just not the blocks with mass. Now we have something else, whether it's the pulley or the string of the rope, string and the rope in this case of the presentation. But in the homework and the questions we've been asked in the class thus far have been all oriented to maybe the pulley has mass or something like that. So I thank you for watching. I hope you enjoyed the video. Thank you so much.